Hi, Molly.
It's going to go on YouTube and it'll be public, so don't be too silly.
Have you seen YouTube?
Huh?
Have you seen some of the stuff on YouTube?
Yeah, but I try to be semi-serious when I'm doing this. Okay, so this is where we were at the end of the hour last time, right? We had esterified our fatty acid to coenzyme A, but there isn't a fatty acyl-CoA carrier across the mitochondrial inner membrane. So we transferred that fatty acid to a carrier molecule called carnitine, and we showed the structure of carnitine last time. Right? The carnitine acyltransferase more generally, right? So there's one in the cytoplasm/intermembrane space. There's a carrier for the fatty acylcarnitine that brings the carnitine in as free carnitine goes out. So it is what kind of carrier? It's an antiporter. Facilitated or active?
Facilitated.
Facilitated, right? So we have a facilitated antiporter. And then within the mitochondrial matrix, there's another version of the carnitine acyltransferase that transfers the fatty acid to a new molecule of CoA, makes the free carnitine. And so it's the exchange of free carnitine and fatty acylcarnitine that is going on. So as fatty acids are being oxidized, right, this product is being removed, pulling this process this way, so as carnitine goes out, new fatty acylcarnitine is coming in. Okay? So that's where we were on Wednesday. Yes? Any questions about that? And so now we were ready to talk about the fatty acid oxidation step. So fatty acid oxidation then starts with that fatty acyl-CoA that we just made in the mitochondrial matrix. Okay? So, we have an acyl-CoA, right? Thioester, right? And so the fatty acid oxidation step goes like this. There is a flavoprotein dehydrogenase that catalyzes the oxidation between alpha and beta to make a trans double bond between alpha and beta. And what enzyme did we say that was analogous to?
Succinate dehydrogenase.
Yeah, succinate dehydrogenase. So this is an FAD-linked enzyme. It is similar to succinate dehydrogenase in that it catalyzes a similar reaction by a similar mechanism. That is, we deprotonate this alpha carbon next to the carbonyl. That allows a hydride to be transferred from the beta carbon to FAD. Right? So it's a 2-electron oxidation. It's different in that the acyl-CoA dehydrogenase, unlike succinate dehydrogenase, doesn't interact directly with Q. There's an intermediate system. There's a system, there are a number of these FAD-linked dehydrogenases, right? Fatty acyl-CoA dehydrogenase being one of them, that interact through an intermediate protein, right? So this intermediate protein links the FAD to the Q. So there's an extra protein step, an extra enzyme step in between. Unlike succinate dehydrogenase that appears to interact itself, right? Succinate dehydrogenase combines these two activities, where the oxidation of the substrate and the transfer of the electrons to Q are done by two different enzymes in this other system. Okay? The other thing you find, apparently, is that, and this is debate, but I think it makes it interesting, there's not just one fatty acyl-CoA dehydrogenase. There are a number. And they differ based on the length of fatty acid they work on. So there's this series some that work on very long chain fatty acids, some that work on shorter chain fatty acids. So, right, as we're going through, it's not always this same dehydrogenase. As this gets shorter, it's passed on to other sets of fatty acyl-CoA dehydrogenases. But the other interesting link, and unfortunately, I haven't been able to follow up on this since it became an issue. There was a time, and I'm not saying this is still the case, but there was a time when some people thought there might be an association between a deficiency in an intermediate chain length fatty acyl-CoA dehydrogenase, I think an intermediate one, and some kinds of sudden infant death. Not all sudden infant death cases, but that some kinds of sudden infant death cases were associated with a deficiency of one of these profiles of the fatty acyl-CoA dehydrogenase. So the thought was that these babies during sleep, while their control systems are immature, would have a metabolic crash while they were sleeping that led to their suffocation and death. Okay? I don't know what's happened to that debate, but there was a debate around that. So if you go back and search fatty acyl-CoA dehydrogenases in SIDS, you'll find stuff. Right? So we get a trans-enoyl-CoA, right? A trans-enoyl-CoA where the double bond is conjugated with the carbonyl. Okay? Now, we're going to add water. Yeah, go ahead.
What does the delta sign mean?
Remember when we named unsaturated fatty acids in the first semester? There was that delta designation for where the double bonds were?
Yes.
Right? So if the carbonyl is carbon 1, 1, 2, so that means the double bond is after carbon 2.
Okay.
Right?
And the double bond is conjugated because of the first step, right?
Right. Just the chemistry makes it conjugated. That's a system. Right? Otherwise we couldn't deprotonate this and have that leak. Right? It's a conjugate elimination reaction. The reverse, right? One of Dr. Stickney's favorite reactions, the Michael addition, right? A nucleophilic conjugate addition. So this is a conjugate elimination, sort of the reverse of that Michael addition. Okay? So we set here, but now you set me up because we're going to add water. Our nucleophilic water is going to add to carbon 3, right? And so this becomes, right, we do a nucleophilic, a conjugate elimination to make our double bond. We're going to do a nucleophilic conjugate addition to add water. And we talked about this when we talked about fumarate. Right? Adding water across the double bond of fumarate. So water as a nucleophile can attack carbon 3. That pushes the pi bond electrons to carbon 2, stabilized by resonance. Then you can protonate that. Right? And so we get another nucleophilic conjugate addition, a pattern we've seen before. Right? And so now we've created a nice secondary alcohol. What can we do to a secondary alcohol? What? Oxidize it to a
Carbonyl.
To a carbonyl. What do we call a carbonyl in the middle of a chain?
Ketone.
A ketone. So we're going to oxidize it to a ketone. And so that kind of oxidation is ready-made for an NAD link. Right? So we've got oxidation to make FAD, to create the double bond. We add water. Now we've created a mole of NADH as well in the cytoplasm. I'm sorry, in the mitochondrial matrix. So in the mitochondrial matrix, these are interacting directly with the electron transport chain. Right? And so now we're down here and we've got a carbonyl with a methylene group and another carbonyl. Right? So here we go. Since this carbonyl can stabilize a carbanion on that carbon, that carbon can become a leaving group. And so this is one of the times that I think your author is a little bit misleading with their color scheme, because in this, coenzyme A acts as a nucleophile in a, what kind of reaction?
Nucleophilic acyl substitution.
Nucleophilic acyl substitution, right? This becomes an acyl derivative with a leaving group on it. But since this is a leaving group, where do those electrons go? With the carbon. So to me, that bond should be black, because those electrons are going and becoming part of the product, right? So coenzyme A acts as nucleophile, nucleophilic acyl substitution, stabilized carbanion acts as leaving group, it is protonated, that creates acetyl-CoA, and then we've got remaining a fatty acyl-CoA that's 2 carbons shorter than the one we started with.
Plus
You just do it again.
Yeah. So what happens to the acetyl-CoA? It goes to the citric acid cycle. So in the citric acid cycle, we get isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase, an ATP directly, succinate dehydrogenase, malate dehydrogenase, right? We get all that cycle. So we get more NADH and ATP from the acetyl-CoA. And as Reed said, our shorter fatty acid either goes back and interacts with the same acyl-CoA dehydrogenase, or if it's gotten short enough, moves on to the next stage, acyl-CoA dehydrogenase. And so the cycle just continues. What?
I didn't realize there's an arrow pointing back.
You didn't see that?
No.
You know, that was just border.
I was like, oh, I figured something out, and no.
Your subconscious was reading the arrow the whole time.
Yeah.
Right? So, it just keeps going. So, if we've got, like stearate, chocolate would be fun.
Do you not need to know the different enzymes? Are they not important? Like the dehydrogenase?
I mean, they're important, but I think they're kind of, I mean,
Like the different dehydrogenases?
no. You mean this one?
Yeah.
No, I mean, that there are, it's long-chain fatty acyl-CoA dehydrogenase, intermediate chain fatty acyl-CoA dehydrogenase, and short-chain fatty acyl-CoA dehydrogenase. Right? It's not that complex. Okay? Now, so, cameraman, so we've got an 18-carbon fatty acid. Right, so if we start with a steroyl-CoA here, right? So we go through one cycle. For every cycle, we get an FAD, right? An FADH2, an NADH, and we end up with right? A coenzyme A 2 shorter plus an acetyl-CoA. Acetyl-CoA is going to go into the citric acid cycle. Right? So we're going through the citric acid cycle. As we said, we've got isocitrate dehydrogenase. We've got alpha-ketoglutarate dehydrogenase. Right, which is also the 2 places we lose our carbon dioxide. We've got the GTP in the succinate thiokinase. We've got an FADH2 in succinate dehydrogenase. And we've got an NADH from malate dehydrogenase. Now we're back to oxaloacetate. We start again. So, as we go through this, it gets 2 shorter, right? So we go